welcome to this special example of watching my dogs go nuts. No, you probably heard that, but whatever. Somebody drove by. Dogs are dogs. So, an optimization example from calculus. Okay, so a light source is located over the center, so it's got to be in the center of a circular table. And in this case, our diameter is going to be 14 feet. So let's just write that in here. Come on. Let's write that in right here at 14. Okay. Find the height of the source such that the illumination eye at the perimeter, so all around the edge, you're playing cards, you want to be able to see your cards, you're eating dinner, you want to be able to see your food. I want the illumination at the outside perimeter of the table to be maximum if our illumination is given by k times sine of alpha over s squared, where s is our slant height from the light bulb to the perimeter of the table. Alpha is the angle at which the light strikes the table, and k is a constant. It's a constant of illumination. Okay, so, wow. As I'm looking at this, I see a couple of things. I see a lot of confusion. First of all, let's talk about our height. Right? If our height is 0, if our light source is down here at the bottom, then our alpha will also be 0. And, well, there's no light source at the edge because it's all in the center of the table. Okay, so let's ignore that height. Let's suppose that it was super high, right? So this is super high. That means that we're going to have it's essentially going to be an alpha that can only go straight up, right? So a kind of infinite table, infinite height. 2 words, I wrote it as one. Infinite height, my alpha would be like pi over 2, right? A 90-degree angle is the most it's going to be if it's over top of the table. And this would be like a huge spotlight over the top of a dinner table, right? Everything's illuminated. So it looks to me like our alpha has to be between 0 and pi over 2. Okay. My height for a 14-foot table, I mean, really, how big of a height are you going to have? You'll have a height, I don't know, I'm going to say reasonable ceiling. I realize we could put tables outside, but a reasonable ceiling height, so maybe about 30 feet. I don't know, restaurants, I don't know, we'll go with that, 30 feet. And that's just for the problem, right? Infinite height is possible in our mind's eye. Okay, well, I also see a nice little Pythagorean triangle here, nice little right angle, height, the slant, half of my table length is 7, and I have an alpha. This leads me to h squared plus 7 squared equals slant squared, but there's no alpha involved. So it's probably not going to be Pythagoras. So instead, what else do we know? When in doubt, use trig. All right, I'm going to write this equation here. I equals k times the sine of alpha over s squared. All right, when I try the Pythagorean theorem first, right? Pythagorean triple, how can we do this? As soon as I looked at the formula and saw sine of alpha, I should have said, hey, think trig. But for some reason, I didn't. I'm going to scroll up now. If we go back and we look over here with our new line of thinking, what do I know about alpha? I know the sine of alpha, sine, opposite over hypotenuse. I know the cosine of alpha. Cosine of alpha is adjacent over hypotenuse. And I know the tangent of alpha. Tangent of alpha is opposite over adjacent, so this is h over 7. All right. This is probably okay. We can, from this one, right, we can multiply both sides by s, and we get h equals sine, s times the sine of alpha. Not really helpful. We can solve for s. And this will be, excuse me, let me move our cursor around here. Get that out of the way. There we go. We can solve this equation for s and get h over sine of alpha. That's not really helpful. We still have 3 variables in all of these. Okay, moving on. S here, right, because that's the only thing I'd want to solve for, would be, because there's no h, 7 over cosine of alpha, which is also known as 7 secant alpha. Well, that's not too bad. I could write s entirely in terms of alpha. Oh, well, look at this one. The tangent doesn't involve the s. The cosine doesn't involve the h. While sine is nice, h over s, these other two are going to end up being quite important. Because what I'm able to do now is using our trig functions, looking at alpha as our focal point, right? Because alpha, the angle of alpha is kind of going to determine our height here. And vice versa, the height determines our angle. If I can rewrite everything in terms of alpha, so I can replace my height, I can replace my s, I only have to replace s. Look at that. Here we go. I know that this is going to be k sine of alpha over, instead of s squared, this is 7 secant of x squared, which I'm going to rewrite as k sine of alpha over 49. My goodness, really? Did I just do that? See, normal people right here would go back and rewind and, like, you know, edit. No time for that, my people. No time for that. This is k over 49. Remember, k is a constant. It's just a number. For German, constant, I believe, is why we use k. K over 49, sine of alpha. And if I have a secant squared in the denominator, that's known as cosine squared alpha, right? So let's use our standard trig functions. So what we've done is we've taken our original, let me annotate this a bit. This is our original function. Also known as our primary equation. This is the one that we want to maximize. Over here we have all sorts of secondary equations. And these secondary equations, I'm going to put them all in a little bracket here. These secondary equations help us get to an explicit equation in terms of a single variable. And that's what we're looking for here. All right? We had to find some way to get this down to a single variable. K is just a constant. It's just a number we call k. It depends on the light and the source itself. Okay, so I want to now maximize I equals k over 49 sine of alpha cosine squared of alpha. And yes, I can write better. I just evidently choose not to. Let's do this in a nice purple. We take the derivative. Right? The derivative, k over 49, that's just a constant. Right? Constants come out in front. So here we have two functions being multiplied together, right? Sine of alpha and cosine squared of alpha. So our product rule is in play here. So we'll have first sine of alpha times the derivative of the second. The derivative of cosine squared is 2 cosine alpha times minus sine alpha. Reminders that the minus sine of alpha is the derivative of the inside. That 2, that's the derivative of the outside. And the cosine is, leave the inside alone, in my, my spoken version of the product rule. So first, derivative of the second, using the chain rule, plus second, derivative of the first, derivative of sine is cosine. And let's tighten this up a little bit. I prime is k over 49. Notice they all have a cosine of alpha, so I'm going to take out a cosine of alpha as well. Now I'm left with 2 and a minus and a sine squared. Alpha, not x. Yeah, I know. I tried to be a cheater. Sine squared of alpha plus cosine squared of alpha. That is one big parenthesis. And everything in me really wants to make that better. I don't like that minus 2 sine squared of alpha right here. We have cosines mixed with sines. You know when we're trying to solve those, that doesn't work out well for us. So let's go with a lighter blue over here. Keep in mind our Pythagorean identity. I can replace cosine squared with 1 minus sine squared. So then when I'm looking at cosine squared alpha minus 2 sine squared alpha, that becomes 1 minus sine squared alpha minus 2 sine squared alpha, which is I prime is k over 49 cosine alpha times 1 minus 3 sine squared alpha. Okay, so let's review page 1. So we have this light over top of this table, and our angle alpha totally depends on the height of the light, and then that's also going to determine our S value here. Now most people are looking for this is the ceiling, here's where I put the light. But think of this as on a chain, right? You want to make it so your table is illuminated all around the side. But we first see Pythagorean theorem. Not everything is straight Pythagoras, so we got to get a little tricky with it. Oh my goodness, I just came up with that. And it's a shame that like 7 people in all of recorded history are going to hear that. Okay, to get tricky with it. Okay, so instead we look at the trig relations. Right, looking at alpha, centering here on our angle alpha, we have the sine, we have the cosine, and we have the tangent. So sine, cosine, and tangent of alpha. And with that, we can solve for the other variables as well. We're not going to solve for alpha. Nobody's going to choose to do inverse trigonometric functions until they have to, right? We'll save those to the end if needed. Once we have our substitution of variables, we have our entire group of secondary equations here that I've bracketed off in orange. Given our original equation and our newfound relationships, we can rewrite our illumination equation in terms of just alpha, right? So alpha is our only variable. This says alpha, only it looks like I wrote it as an x. I apologize, that should be an alpha. Instead of calling it 7 secant of alpha squared in the denominator, that 7 squared became the 49, and instead of a denominator of secant squared, we have cosine squared. And we have our I in terms of our single variable. So that was just reading the table, figuring it out, putting all together what we know in order to get an equation we can deal with. Because the actual calculus of it is easy. Right? The actual calculus of it ends right here. It's just one line of calculus. Okay, but now we know, right? We know that the maximum will occur at critical number. So this will happen when the derivative is 0 or the derivative does not exist. There's, other than 49, we have no denominators going on here that's going to mess it up. Everything should be cool. So we don't have to worry about that one. 0 equals k over 49 cosine of alpha times 1 minus 3 sine squared of alpha. Leads us to, all right, k over 49 is not going to be 0. Multiply both sides by 49 over k, whatever. Cosine of alpha equals 0, or 1 minus 3 sine squared alpha is 0. Now, if cosine of alpha is 0, then alpha must be a pi over 2 multiple, an odd multiple of pi over 2, right? In the interval from 0 to 2 pi, it had happened twice, but we know 3 pi over 2, this is 270 degrees, right? We're not talking about light source from that far away. And even this 90 degrees, right, we've decided we don't have an impossibly high light source, so the 90 isn't even possible. That's outside of our given domain. We talked about it earlier. All right, so neither of those are useful. Here, we'll have the sine squared of alpha. Let's subtract 1, divide by 3. And when we take the square root, sine of alpha is plus or minus the square root of 1/3. The square root of 1 is 1. Let's call it what it is. But we know alpha is acute. So I know that sine of alpha, my goodness, I just can't actually write that all in order, so let's try again. Has to be 1 over square root of 3. It can't be the negative one. Negative angles, that's over in quadrants 2 and 3. Nope, I lied. Quadrants 3 and 4, sine, right? But it's an acute angle, so we don't even have to worry about quadrant 2. We're only looking at quadrant 1 here. Now, this is the only information that we have. We don't know what alpha is, but we know about the sine of alpha. And let's check it. Right? If we know what sine of alpha is, we also know what cosine of alpha is. I'm going to bring us back to an original color here. If I have a frustration for my pen set here, if I have any angle in quadrant 1, right, any angle in quadrant 1, so that the sine of that angle, opposite, over hypotenuse, is 1 over square root of 3. I can find my x value. And we happen to know x squared plus 1 squared is the square root of 3 squared. X squared plus 1 is 3. X squared is 2. So my x must be the square root of 2. And what this tells me is the cosine of alpha. Cosine of alpha is the square root of 2 over the square root of 3. It tells me tangent of alpha also. Now, I know this is either going to be a minimum or a maximum because the problem asked me to find it. And so when I do my test intervals, I might do a test interval from 0 to 1, right? Because as alpha goes from 0 to pi over 2, sine of alpha goes from 0 to 1. So I might even do test intervals on the sine of alpha because our original k sine alpha over 49 secant squared alpha. I know I've had way better recordings in my life, but I'm not going to do this one again. I'm sorry, it's long. We could test it in here, right? I mean, this is always going to be positive. That's going to be positive. So when we have it from 0 to... Pick a number to the left of 1 over square root of 3. Pick a number to the right of 1 over square root of 3, and we could determine the sine. K over 49 is always going to be positive, as long as k is positive. Cosine squared is always going to be positive. So the sine... oh my goodness, I'm going to stop talking. Maximum here. And if this is the maximum, then our h value, which we know to be 7, our h value, which we know to be 7 tangent of theta, is now equal to 7. The tangent of theta is sine divided by cosine. My 2's are looking horrible today. I apologize. That's a 2. So this is either 7 over square root of 2 or 7 square root of 2 over 2, and this will be feet. So we know exactly where to put that, and I'm curious if I had a 14-foot table, 7 divided by square root of 2, Well, for this particular type of light, you only need it 5 feet above the table for you to be doing good. All right, so my students, watch for this one. It's a great problem, and it might, hint, hint, be on the exam. Thanks for listening.